Alright, so in this video I'm going to be explaining another important paper with the title Structural Entropy Guided Graph Hierarchical Pooling. This paper in ICML 2022, which uses this idea in 2016. So following the success of convolution and non-Euclidean space, the corresponding pooling approaches have also been validated on various tasks regarding graphs. However, because of the fixed compression quota and stepwise pooling design, these hierarchical pooling methods still suffer from local structure damage and suboptimal problem. So, inspired by structural entropy, we propose a hierarchical pooling approach to tackle the two issues. Specifically, without assigning the layer-specific compression quota, a global optimization algorithm is designed to generate the cluster assignment matrices for pooling at once. This is the architecture of the proposed ZEP operator combined with graph neural network. The graph neural network consists of message passing layers and hierarchical pooling layers. A separate algorithm is proposed for cluster assignment generation. So we have this graph neural network, and then hierarchical pooling is a graph coarsening process to dig out a subset of representative nodes and form a new graph. So let's S sub I denote the cluster assignment matrix at i's pooling layer, where n sub I and n sub I plus I are the number of nodes before and after graph coarsening. The new adjacency matrix and node feature matrix after pooling are calculated by the next equations. So according to this cluster assignment, P sub I plus 1 receives the node hidden feature H sub I and merges these features to refine the initial representation for N sub I plus 1 clusters in the novel graph. So they do cluster assignment via structural entropy minimization, that paper that in 2016 that I said. So let the two tuple be a graph. The formal equation of structural entropy can be written like this. Now here, V sub t is a non-root node in T that can also be viewed as a node subset according to its leaf node partition in T. So the minimum entropy realized by optimal coding tree is the structural entropy which follows the target equation. Besides optimal coding tree that realizes the minimized structural entropy, a natural coding tree with a certain height is preferred. So the k-dimensional structural, this is the k-dimensional structural entropy of G, is proposed to decode the optimal code tree with a fixed height k. So under the guidance of k-dimensional structural entropy, we aim to investigate the solution for decrypting the coding tree with a certain height k. So they have some, let's say, operators, remove, merge, and these things. But this is the runtime complexity of the algorithm. It's order of 2n plus hm log n. And so first stage with bottom to top construction. Then the second stage is compressing the T, the coding tree T, to certain height k. And the third stage is to fill the tree to avoid cross-layer links. I don't think it is bio-inspired. Then we do graph classification or node classification as well. Then they compare it with top K pool, min cut, because it's hierarchical pooling, so they compare it with these state of the art. And you see the essential structure preserving in mutag, finding the mutagen molecules. You see the essential structure. Maybe the min cut pool only selects this part instead of having something meaningful. So this one, it looks more interpretable. And then we have data sets for bioinformatics and social networks that they see graph classification accuracy. And they compare, for example, with graph convolution with their hierarchical graph pooling. For example, from 3% improvement here and 6% improvement here. But they also compare with global pooling. So hierarchical pooling, if you compare with global pooling, you see it's very close to each other. All of these are very close to each other.